This video is about limits and numerical tables, and this is an introductory discussion on limits in the context of calculus. This is not the first video in this topic, but it's building on what we've already seen with graphs and notation and concepts. For our notes about numerical tables and limits, we'll start by saying this. Characteristics and cases of limits we see graphically, so we've already seen a lot of cases of how limits can show up on a graph or not show up. But these characteristics and cases also show up numerically in a table of values generated by a function. Now, since a table will only give us the discrete level of precision corresponding to the quantity and quality of input values we choose, we will produce enough confidence to guess the limit result within reason. Alright, so there's a little freedom here, but that's not a bad thing. I think it'll help us understand the concept of a limit even further. Let's consider an example where we want to guess the value of the limit, if it exists, by evaluating the function at the given inputs. Now we say guess in quotes here because really it's a very educated guess. We're not just kind of throwing a guess out here from a picture or just simply by looking at a table. We're understanding the table values we see in the context of what we already understand about the definition of a limit and how it works graphically even. Consider this example. We want to find the limit as x approaches -3 of the rational function given where the numerator is x squared minus 3x and the denominator is x squared minus 9. So we will still yet learn other ways to dive into a function like this more algebraically or analytically, but for now we're just looking at the table. Now what I have shown here is a table of values generated. This could be generated with a graphing calculator, just a regular TI-84 plus graphing calculator is kind of the standard one we're using right now. And you'll notice the x inputs, but they're not like standard integers or whole numbers. They seem to be a pretty specific set of input values. Now, I want to focus in at the middle of this table and then see if we can understand why these certain inputs were chosen. If we consider what we're trying to find here, notice we want to find the limit of this function as x approaches -3. Now remember, what we discussed in the notation is that when you see x approaching -3, that really implies two things. It implies x is approaching -3 from the left, and it implies x is approaching -3 from the right. We already discussed that when you have these superscript symbols of minus and plus signs, that means you're approaching from a certain direction. But in general, when you just see a limit for x approaching -3, you assume it's approaching from both ways. Well, in a table, we need to understand or be able to represent both of those directions with specific input values. Let's consider these two directions and how it might influence our table. When x is approaching -3 from the left, if it helps, even maybe draw out a number line of what that would look like. If you just put -3 on a number line and you're approaching it from the left, those would be walking through values that are less than -3. So notice in our table, we start with input values of -3.5, -3.1, -3.05. Those values are walking on the number line toward -3 from the left. They're less than -3, but they're increasing, getting closer to it as they go. So that's what's happening when we walk through these input values. Notice they're decimal input values, and this is where you have a little bit of freedom. As it said in our notes, we want a certain level of precision that will help us guess this limit with confidence, but there's not only one way to do these inputs. I've picked -3.5, -3.1, -3.05, but the point is they're increasing, getting closer to -3. So we'll continue that down toward -3, and notice they get pretty close to -3. I have -3.01, -3.001, -3.0001, and then finally we have -3, the target value in the table. But notice that these values are getting closer and closer to it Now, as we consider the second case where we are approaching -3, but this time from the right, again, let's kind of just think about a number line, and if -3 were plotted on it, if I'm approaching it from the right, then I'm using values that are actually bigger than -3, but they're decreasing as they get closer to it, right? From right to left on the number line, values decrease. So notice now below -3 in our table, at the very bottom, we start with this -2.5. That's clearly to the right of -3 on the number line. And then these values start to walk their way toward -3. These are actually decreasing values, but I'm using a level of precision that is kind of symmetrical with the values that we're approaching -3 on the other side. If I read up the list of these inputs, you'll see -2.5, -2.9, -2.95, -2.99, -2.999, -2.9999. Okay, so they're getting closer to -3 from the right. That is, they are decreasing values as we list them, moving toward the -3 in this table, but they're approaching -3, and they're getting more precise as they go, as you can tell by the number of decimal places given. Now you'll notice in the table, which would be generated by a graphing calculator, that there's an error at the input of -3. So think through what that means for a second. If you look back at our function, the denominator is such that if x were actually -3, then the denominator would have -3 squared, which is 9, minus 9, but that would be 0, and that's a problem. The function would not be defined there. We'd be dividing by 0, which is why the calculator gives us an error. Now, the good news is we can actually work around that. If you remember back to the notation and concept of a limit, we were very, very clear about this arrow referring to a specific word, and that word was approaches. And as you saw in many examples, a function does not even have to be defined at a certain value for it to have a limit there. And this is a case where the function is not defined at -3. Now that doesn't mean that the function does or does not have a limit there automatically. It just simply goes to show that the notation works, and the word approaching is kind of illustrated with all these decimal values that are getting closer to 3, but not quite actually there. In fact, we can't get there with this error. Now, let's observe what's happening with the output values, in other words, the f of x values for all of these inputs. If you look now at the right column of this table, when we started with our input of -3.5, and then we worked our way closer to -3, notice that the input values are starting to increase. So the inputs read in corresponding order here: 7, 31, 61, 301, 3001, 30,001, and then that leads us up to the error spot. But notice that those values are increasing very clearly here. Now, if we go below the error, where we started at the bottom of our table, when we started with an input of -2.5, the output was -5. And then as we work our way up toward the input of -3 in the middle of this table where the output was an error, notice what's happening to the values. So it started at -5, then -29, -59, -299, -2,999, -29,999. Okay, so clearly the values are decreasing pretty drastically. And as we get close to our input target of -3, remember the function's not defined there because of the error shown. As we approached -3 from the left, that was the first set of values, they were increasing pretty drastically. So let's just guess for a second that that would continue to happen even if I used more precision, right? The last input I used before I got to -3, approaching it from the left, was this -3.0001. What if I had gone out even more precisely, like -3.00001, or you name it? I mean, you can keep going as precise as the calculator will let you. But you can expect that these values would probably continue to increase, and you can verify that until you're confident enough. So we're going to go ahead and guess that these values are approaching a positive infinity as we approach -3 from the left. Now, if we go below in the table where we had the other values going, notice those were getting more and more negative. And similarly, we'll suppose or guess that maybe they approach negative infinity. You can verify that with more levels of precision if you use inputs that are even closer to -3. We had -2.9999 as the last one. You could add more nines to that as much as your calculator would let you and find more precision there. But I think this is a fair amount to be able to educate and guess what's going on with this one. Now, what we're seeing in this table with those guesses is that the limit as x approaches -3, the first set of values we did was from the left of our function. I'll just call it f of x instead of recopying that rational function. It seems like that limit was probably infinity. That's what we had discovered in our table. But then it also seems like the limit as x approaches -3 from the right, that was the values we had listed below in this table, seem to, of our function f of x, seem to approach negative infinity. And in this case, which we've already discussed in our definition, this would be where the limit does not exist. When they approach different infinities, there's no way to summarize them with one symbol. So we'd have to say DNE for does not exist. So this is a way we can use even a table of values to verify this kind of limit, or that it doesn't exist and how it doesn't exist.